In section 2, we're going to be learning how to calculate the pressure in fluids. So here in this picture we have a, cylindrical glass container, and it's full of water. And the water in that container is exerting pressure on every part of the container that it's touching. So of course on the bottom is holding that liquid up. So clearly the bottom of the container is applying a force to the liquid. And it's not so obvious that there's pressure on the sidewalls, but there is. The easiest way to think about that is if I were to put a hole in the side of this, the liquid would be flowing out. So the container is applying a pressure to keep the fluid inside. So of course we know from Newton's third law, that every force is an equal and opposite reaction force. That means the fluid is also applying a pressure on the side of the container. Now pressure is a force that's applied over a specific area. So the units of that are going to be newtons divided by area, which is meters squared. And it's important to know that the pressure of the fluid is everywhere and in every direction. So we use pascals in physics. As I said, that's newtons per square meter. And that's the SI unit, but there are lots of different units, even more so than what we've had to deal with in the past, with speed being miles per hour and we're using meters per second. When it comes to pressure, it seems that every discipline has their own units that they like to use. Most commonly used unit is the atmosphere. That's the amount of pressure resulting from the atmosphere of the Earth. And it's 101 kilopascals. Another unit of measure is the millimeters of mercury. This is used by chemists mostly, and here's the conversion for that. We really won't use that, but this table is just to give you an idea of the different units that are used for pressure. Inches of mercury is used by our weather forecasters on TV, and of course, if you go get the air in your tires, you know that's pounds per square inch. Most United States engineerings will use pounds per square inch. So yeah, it's kind of frustrating that we have all these different units. We will be using in this course pascals, and because the atmosphere is so pervasive here on Earth, we're also going to you have to know what an atmosphere is, and it's this 101,000 pascals. And it's on your equation sheet. So what's interesting about fluids is the deeper the fluid is, the more pressure there is at the bottom of the fluid. So we use this equation. The total pressure in a fluid is equal to the ambient pressure, that's the pressure at the top of the fluid, plus the density times gravity times the depth of the fluid. The easiest way to explain this is to imagine a stack of books. As each book gets put on top, the deeper the stack of books, of course, the heavier all those books are. That means there's going to be a larger force on the table over the area of that book. So clearly, even if you're talking about books, the pressure on the table is proportional to the depth of the books. So this is exactly the same. The deeper the fluid, the more fluid there is stacked on top. That means it's going to require a larger force to support that weight. And pressure is force divided by area. So the larger the pressure will be. So this pressure is hydrostatic pressure. We're only going to be calculating pressure of fluids when they are not moving. So our first example is to calculate the pressure on a submarine, because clearly submarines go deep down into a liquid. So as they go deeper, the pressure on the submarine is going to increase. We're just going to calculate it, and we're going to give our answer both in pascals and in atmospheres. And we're told the density of seawater is 1030 kilograms per cubic meter. So if we're asked to calculate pressure, we're going to use the equation we were just given. Total pressure is equal to atmospheric pressure, because that's what's on top of the water, plus the density of the liquid times g, that's our gravitational constant, times the depth of the liquid. So if we substitute in what we know that 1 atmosphere is 101,000 pascals, and the density of the water we're given, 1030. There's our G, we already know, and there's the depth of the water. They're sitting at a depth of 300 meters. The most common mistake on this type of problem is to omit the ambient pressure, but it's very important to keep that in the equation because it's a major part of it. At 300 meters, you end up with a large component from the water itself, but you can't ignore the pascals of the atmosphere. So this adds up to 3 million pascals. Now if we want to convert that, because we're asked for pascals and atmospheres, if we want to convert this to atmospheres, we're going to need to divide by that ratio that 1 atmosphere is 101,000 pascals. So that's going to be, we're going to use our straight line method. So there's our pascals. We'll draw our straight line. And we know that 1 atmosphere is 101,000 pascals. So that's going to cancel the pascals, and we're left with just 30 atmospheres. Now that's a lot of pressure, but 300 meters is pretty deep. So another thing that's important to know about fluids is if you change the pressure at any one point in the fluid, it's going to change the pressure at every point by the same amount. Now that's Pascal's principle, and it's very important for things like hydraulics. We're not going to do much with it other than maybe calculate. So as we're learning to calculate the pressure in liquids, it's important to know that at the same depth, the pressure is going to be the same. Now, the key word there is in all open regions. As you'll see in a minute, it's not necessarily the same pressure if it's closed, but we can use this horizontal line. So at the same depth, all of the pressure at that liquid will be the same. And it doesn't really matter. So what this is showing you is it doesn't matter what the shape of the container is. The liquids will always rise to the same level. So here it looks like maybe this pressure might be less because the shape is different, but it's not. As long as the depth is the same, the pressure is going to be the same. So when we're calculating pressure in liquids, the easiest thing to do is draw a picture. Then we're going to be sure we mark that atmospheric pressure at the top of the liquid, usually 1 atmosphere unless the problem tells you otherwise. Then we're going to use horizontal lines. And the horizontal lines are used because we know the pressure along any horizontal line is going to be equal. Then at some point we're going to use our hydrostatic pressure equation. Total pressure equals atmospheric pressure plus rho dg. One thing to keep in mind, some of the homework problems may ask for gauge pressure. Gauge pressure is defined as the pressure above atmospheric pressure. So here's our first check. Here we have 2 points in this shape. One of the points is under an open region. The other point is under a closed region. What's the pressures at these 2 points? What do you think? Yeah, the pressure is equal because there's a horizontal line. If you drew a horizontal line, it would go between both of these. So even though the depth here underneath that closed section looks different, because there's a horizontal line, the pressure of these 2 points is equal. They're at the same depth relative to this open area. So here's another example. We've got a tube and it's open, and then on this side it's closed. We're going to calculate the pressure at the top of the closed tube. So again, we've got our picture drawn for us, and I've got the horizontal line already drawn. So if we're wanting to know the pressure here, we'll draw a horizontal line, and we know that the pressure anywhere along this fluid, along that horizontal line, is going to be equal. So I'm going to use the equation, total pressure equals atmospheric pressure plus rho GD. And here, when we've got this horizontal line, it's really easy to calculate what the pressure is here underneath the open region, because we know it's going to be atmospheric pressure up here, and then we just increase the depth going down. So if we substitute in what we know into this equation, there's our atmospheric pressure. So in this next example, we are asked to calculate the pressure up here in this tube. So we have a tube that's open on one end and closed on the other. We're asked to calculate what's the pressure here at this closed end. The liquid is 100 centimeters deep below the open end and only 40 centimeters deep below the closed end. And we're told the density of water is 1,000 kilograms per meters cubed. Reminded, maybe I should say. So we're going to calculate the pressure. So the drawing is already done for us. And if we're wanting to calculate the pressure here, I'm going to use the horizontal line method because up here we don't know what the ambient pressure is. So I'm going to use the horizontal line and draw it here. So the pressure here at this closed end is going to be exactly the same pressure as it is over here in the opened end at the same horizontal place. So once we draw a horizontal line, then we can use the equation for our static pressure. Total pressure is equal to ambient pressure plus rho GD. So then we can start substituting in what we know. So we're looking for the total pressure, and below the open end, we know that that's an atmosphere. So we'll put in 101 pascals for 1 atmosphere. It's open to the air. Then we've got the density of water, 1,000 kilograms per cubic meter. There's our G, and then the depth. Now the depth is not clearly marked, but if this opened end is 100 centimeters from the bottom and the closed end is 40, then it's not hard to deduce that the depth here at this place is 60 centimeters, and that's going to be 0.6 meters. So once you substitute everything in, you know, and again, very important to keep your units, we can go ahead and calculate that ends up being 110 pascals. If you like atmospheres, you can divide by the 101,000, or it's about 1.1 atmospheres. So here's another quick check for you. Let's see if you can get this one right. So we've got 3 different points. Point 1 and 2 are under the open section, and point 3 is under the closed part of the container. What can you say about the pressure of these 3 points? Yes, so this one up here at the top is going to have less pressure than 2 because it's at less of a depth. Points 2 and 3 are along a horizontal line, so the pressure along that horizontal line is going to be the same. So the pressure at point 2 and 3 are exactly the same. So you can't get by pressure in fluids without talking about atmospheric pressure some. So I really like this picture because it shows up at really high altitudes, the air is really thin. And as you get deeper into the atmosphere, the pressure increases. But because our atmosphere is a gas, an increase in pressure will actually push those atoms closer together. And you can see that here in the picture. So up in the atmospheres, pressure is really small. Those atoms are stretched apart. The deeper you go, the more the pressure pushes the atoms together. And then as you get close to the Earth, that's really, really dense atmosphere. As you remember, we calculated 72 kilograms of air in a room. That's not a small amount of mass. And what's interesting is 99% of the air in our atmosphere is below 30 kilometers. So if you look at pictures of the Earth, it looks like the atmosphere is fixed around the Earth at a very specific depth, but in reality it's not. It's a gas, and it goes up quite a ways. But most of it is pretty close to the Earth. And of course, if you've ever seen a weather forecast, and who hasn't, you know that atmospheric pressure changes because the Earth is spinning. So you end up with winds on the Earth, and that wind, we're not calculating that type of pressure, we're only doing hydrostatic. But it's important to know, as the wind blows, it will change the pressure at local places. And so your weatherman will tell you areas of low pressure and high pressure. And of course, those low and high pressures affect the weather in those areas. So it's important to know a little bit about atmospheric pressure and what these, how that works. But we're not going into this in depth. So there's lots of ways you can try to measure atmospheric pressure. One is with a barometer, and you fill a closed tube. This looks like a very small tube, like a test tube. and you put your finger on it so the water stays in, and then you put it into the water. Now, we've all done this as a kid playing in the bathtub. You know, if you put something, or when you're washing dishes and you put a glass upside down, you can pull water up above the water level so that it looks like this. So part of the sink or the bathtub is at atmospheric pressure, and what you have filled with water will raise the water level above that. And the only reason we're able to do that is because of the atmospheric pressure pushing on the surface of that water. So as you have something filled with water, and of course this shows that test tube with a vacuum on top, eventually if you raise it tall enough you will get that vacuum on top. But we can guess by atmospheric pressure that it's going to have to be quite tall. It will not happen with a glass or a test tube. You won't get a vacuum on top. But if you pull this high enough, you can. And this is one way of measuring the atmospheric pressure, because you know that the atmospheric pressure is here at the bottom, and as you pull this up, the pressure will decrease and decrease and decrease, and at some point the pressure at the top will be zero. And when you get to that height, the height of this pillar of liquid will be equal to the atmospheric pressure here, because we know at this horizontal line all the pressures will be equal. So here on this side we have atmospheric pressure, and on this side we have a known depth and a known density. So we can calculate the pressure due to the liquid on this side, and that will let you measure atmospheric pressure. So the key concepts from this section is that pressure is equal to force over area. Pressure in fluids, that's gases or liquids, press in every direction, not just down, but every direction. And we also learned that pressure will increase as the depth of a fluid increases, and this is our hydrostatic pressure equation. Total pressure is equal to our ambient pressure, most of the time this is 1 atmosphere, plus the density of the liquid times gravitational constant G times the depth of the liquid. And as I said, P naught is usually atmospheric pressure, 101,000 pascals. At one depth along the horizontal line, the pressure is the same regardless of what is above that line. So we will use this in order to calculate pressure in liquids. And that's the end of section 2. We will move on to section 3.